Okay, good morning everybody. I hope everyone's having a wonderful day. So I want to remind you before we get started, actually first, before we get started, are there any questions or concerns out there? I just want to make sure if there's any questions out there. I'm happy to answer anything. But if we're ready to talk more about binary search trees, give me 2 thumbs up. 2 thumbs up. Awesome, awesome, awesome. Okay, so last day we were talking about how we can perform different operations on our binary search tree, right? So we talked, for example, about how we can find or search in a binary search tree, such as using the get operation. We talked about insertion, as in the put operation. We talked about how we can delete in a binary search tree, such as through the remove operation. And we've seen some others, like we did the analysis for smallest. And all of them had worst case big O of the height time. Now, this is where, as I was alluded to last day, where I kind of just said, okay, well, we don't really know what's going on with the tree. We're at the mercy of the structure of the tree, so now I'm going to get more precise about that. So that was a bit of the bad news I had for you last day. So I want to be a bit more precise now about this. So these are 2 trees I've drawn here. These are 2 binary search trees. The one on the left is what we would call a balanced binary search tree. Notice that all of the levels of this tree are filled up as much as possible, but the only thing that might differ, possibly, is there might be some extra nodes down here on the next level, but no more than that. So that means that the level of the leaf nodes can only differ by 1 level at most. This is what we would call a balanced binary search tree. Now, the height of such a binary search tree is going to be exactly equal to log base 2 of n plus 1, where n is the number of records. Because at the end of the day, we want to know what's happening with either the number of nodes or the number of records. Note that if ever we talked about the number of nodes in this representation, it only differs by roughly a factor of 2, a multiplicative factor of 2, right? Because all I'm doing is I'm adding in an extra level at most on every one of the nodes that has a record in it, correct? So if you ever look trying to find out how many nodes there are, you'll find that these formulae are pretty common to modify. But, so this is what we would like to imagine the binary search tree to look like, right? Something like this, where its height is big O of log n. So what would be the consequence if the height of the binary search tree is big O of log n? What would be the consequence of that based on the things we talked about earlier? So what would that mean for us? Anybody have any suggestions? So what would that mean if I gave you for example, a balanced binary search tree, but even just one where the height is big O of log n? What would it mean for us? What would be the consequence of that? And think back to when we were thinking about how, oh yeah, we can think of the binary search tree using the idea of binary search, right? So what does it mean for all these operations? Yes, it is also big O of log n. So wherever I had big O of the height last day, every single time that I did that, it's big O of log n. So do you see where we're going with this? Is that I would like to have it so that the height of this tree is something like that, because there's one problem with our binary search trees, is that they can degenerate. What do I mean by this? Is you can have it where a binary search tree looks something more like what I have on the right. On the right, we would call this a degenerate binary search tree. And the reason why is because we would like it to have structure that looks something like this. It doesn't have to look like this, but we would like it to be like this, just like we imagine this like binary search. But the problem is that you can create binary search trees where it's just a single chain of internal nodes, where each one has a dangling leaf child or a right child, respectively, if you want to mirror this. Where, notice here, all I've done is I've suppressed every one of the records into a single chain, and this should remind you of something. What data structure, if I were to just say, get rid of all of the leaf children that are on the left, if I get rid of all of these, what should this remind you of? Not necessarily an array, but you're very it's like you have to imagine this, that all of our searching and our insertions and removals are going to degenerate into a linked list. Yes. So just imagine you have a list where you have no access in between. You have to do a linear search through all of the nodes. And this degenerates to the case that we talked about when we first started talking about dictionaries, right? Where we had the linked list. It turns into that. That's why we call this a degenerate binary search tree. Is that we say a binary search tree is degenerating when it starts looking like a chain like this. When this happens, it degrades the performance of the binary search tree. So it's okay if you have it where it's maybe not perfect like this, but something that's closer to this is much better for performance than something like this. Is that clear, everybody? So now this is the kicker. So you know how we talk about big O of the height for all of our time complexities? Now, I didn't ever state the time complexities in terms of the input size, right? Well, the true worst case time complexity of all of these operations we talked about last day, all of them are big O of n for a general binary search tree. That's the bad news, just to give you a recap. So this is the worst case for a binary search tree. So wherever we had big O of the height, the true complexity with respect to the input size in the worst case is big O of n. This is because it forms a chain like this, and it can always bound the height by the number of internal nodes. This is a property that we actually have. I told you we're going to use this. We're going to actually use this again sometime later today. But the number of internal nodes is exactly the number of records, right? So, and that's exactly what matches this case. So are there any questions about that? So this is the bad news I have for you. So this is the worst case. The best case that you get is the logarithmic behavior. So this is what you'd get out of the best case. So you get log n for best case, worst case you get linear. Now, that isn't the end of the story though. That isn't the end of the story at all. And you know how I talked about the idea that we don't necessarily even have to have the tree balanced in the most purest way that has this height that's exactly equal to this. What normally you'll find is people would like to have what we call balanced binary search trees. Now this is the purest form of a balanced binary search tree. But some people would like to have something that's like it being balanced. So what we're going to do is we're going to give up. So this is what we're going to do is we're going to give up about a constant factor on this logarithmic term. So we're going to aim for big O of log n height as opposed to just this right here. Now I must stress that there are ways to actually create these types of binary search trees. For example, one thing you can also do is you can take every one of the records you have, insert them into an array, sort it, and then you do something akin to binary search where you start in the middle and you insert every single element from the centers of each subarray. And you can actually build up a balanced binary search for this way, but doing this is slow. It's expensive to do if you absolutely need to do this. So I want to show you that you can actually get this time complexity of big O of log n in the worst case by other means. So to do this, I'm going to aim for a height that's big O of log n as opposed to just purely the ceiling of log base 2 of n plus 1. So this brings me to the first definition for today. Actually, technically this is the third, is that of the notion of height balance. So we say a tree is height balanced if the height is big O of log n. Some people colloquially just say that the tree is balanced if they say it's big O of log n. So if ever somebody's saying, oh, well, is the tree balanced? Sometimes they actually are saying height balanced. So often you'll see me say the same thing here. That's usually what we mean. We want to have the tree so it's balanced. So this is often what people will use as the definition for a balanced tree. But the thing is, there is technically a purest version like this. So we're going to be aiming for big O of log n for the height. Is that clear, everybody? So there's this idea of a balanced binary search tree where you have this exact height, but we're going to be aiming for big O of log n for the height. So if we can make it so that the binary search tree always has height big O of log base 2 of n, as we established, we can guarantee all of these operations will have, worst case, big O of log n time, right? Which is what I told you we were going to try to accomplish. That was kind of like one of our end goals here. So that brings us to talking about what we would do with something like a data structure. Now, like I said, we study these binary search trees, talk about a whole bunch of concepts we have around them. The real question is, I want you to get into the mind of somebody that's trying to study these data structures. So obviously, I can't just take up the person that introduced this data structure and say, this is exactly what they were thinking about. Instead, I would like to just remind you that I basically presented you an interesting question. Okay, we know the best case is big O of log n. And we know the worst case is big O of n, but we have this situation that happens. I would like to get rid of this situation. I want to make sure it always has this height. So this is a very natural question to ask. Is that possible to ensure this occurs? And the great part about this is the answer is yes, you can. So we're going to come up with some ideas to ensure this happens. It's going to be based on the same kind of thing we were talking about the other day. Remember how I talked about this idea that if we have a binary search tree, whenever we make modifications to the tree, we want to make sure it maintains which property? Which is the core property of that makes a binary search tree? What is the key thing that we need for a binary search tree that differs it from just any old binary tree or proper binary tree? Other than the fact that all of our entries or records are in the internal nodes. What's the main property we needed for binary search trees? There's that property, right? The binary search tree property. So we need to make sure that, yes, when we do an in-order traversal of the tree, it makes sure that all the keys are in sorted order, right? So the big thing here is that whenever we made modifications to the binary search tree, before I did anything to it, it was a binary search tree. Then after that, it is still a binary search tree. We're going to see this pattern, this idea of an invariant, pop up in the next couple of lectures. So today and next class, we'll be focusing in on this idea a little bit more. Because when we have a data structure, if we can make sure that we maintain the properties that it has before and after we apply an operation, we can ensure it still has all the properties we would like. So just to give you a kind of a game plan here, because I like to do this with you, is that if I can guarantee that the tree just before I do an operation has height big O of log n, I want to ensure that after I do some operation, after I do that, it also is still big O of log n. Is that clear, everybody? So that's going to be the game plan. I want to make sure that whenever I make a modification to the tree or mutate the tree, we make sure that the height still remains logarithmic. So that brings me to talking about one of the mechanisms for doing this. So I'm going to be talking about a more specialized data structure now, and we're going to specialize the binary search tree. So we're not just going to be talking about just any general binary search tree, which causes this erratic behavior that we have. We either can have it where it looks like that, or it looks like this. By the way, it's very easy to come up actually with trees that look like this. A quick example of how this can happen is if you actually were to try to insert nodes in increasing order. So for example, if you actually put in a sorted sequence, like if you have 1, then you insert 2, then you insert 3, then say 99 and 100, it's very easy to actually create degenerate binary search trees. So you have to be very careful about this. So you can see how there seems to be some relationship in terms of a binary search tree. How we actually try to maintain it actually has a close relationship with the fact that the keys, when you take an in-order traversal of them, they have to remain sorted. So in this case, when I literally give them to you in sorted order and I insert them in that order, it creates really nasty trees like that. But I'll let you think about that. There's a lot of interesting stuff I just sort of brought up. So that brings me to talking about how we're going to try to resolve this question. So I'm going to be introducing you to the idea of an AVL tree. So this was introduced in the early 60s. There was a lot of this kind of data structures work happening in around that same time period. This data structure was introduced by Adelson, Velsky, and Landis, and is actually an example of a self-balancing tree. So I haven't told you what this is, but it actually is exactly the idea I just described. So you know how we had it where I said, oh, we're going to make sure that when I mutate the tree, before if it was, for example, an AVL tree and it has, say, for example, some height, I want to make sure that it maintains that same property before and after I make a change. And the way a self-balancing binary search tree does, as the name suggests, it automatically adjusts the heights to correct itself each time we do an operation. So that should be, that sounds kind of cool, right? So it's going to actually, every time we make mutations, it's going to correct itself. Now it's not going to be, our goal isn't to make a balanced binary search tree in the sense of that purest one I had in the best case. Our goal is just to aim for big O of log n for the height. So to do this, I'm going to modify our binary search tree a little bit. So you can imagine I have a class for my binary search tree. And then I'm going to do is I'm going to inherit all of those algorithms we had from last day. So I'm going to take all of those operations we had, but I'm also going to modify, I'm going to specialize the nodes that we have. So I'm going to define something we're going to call the height of a node. So if I give you the node P, the height of it is in fact whatever would be the height of that subtree rooted at that node. So what I'm saying is if I were to have a tree that looks something like this, for example, if I had a tree that looks something like this, what I'm saying is each one of them will actually store the height of its subtree. So for each one of the leaf nodes, the value should be 0, right? And then I would have, this internal node has height 1, because if I look at this subtree, the height of that subtree is 1. And naturally, the height of this node would be 2. And you could convince yourself that, in fact, the height is 2 based on actually the algorithm we talked about the other day. So we're going to actually use some of the ideas that we actually introduced in that lecture. You know, when we had an algorithm for computing the height, we're going to see how we're going to use that here. So everything sort of rolls around. It's not like magic where I'm just going to magically spoof something on you. It's actually going to be that it's related. So we're going to augment the binary search tree as follows. So for each one of the nodes, we're going to store its current height. Now there's ways to optimize this further. For example, some implementations of this data structure will use the idea of a balance factor, which is just a refined version of the same idea. But I'll focus on the idea that we're just going to maintain the current height. Now, on creation, I'm going to presume the height of a node is 0, but our algorithms are going to allow it to automatically update to be 1 if it is in fact an internal node. So I will talk more about this later. But the point is that our algorithms, when we put them in place for insertion and removal, which those are the only times where we ever mutate the tree, correct? If ever I do searches, I don't mutate anything, right? So all I have to really worry about, and this is all we're going to focus on, are insertions and removals. If we can take care of that, based on our big grand idea, then we can ensure that the height is always something that this AVL tree gives us, which we're going to talk about here very shortly. So the big catch with this, of course, is that whenever you introduce another attribute of some fixed size, you're going to add a big O of 1 extra space, 1 for each one of the nodes. So the total space that's used by this tree will be big O of n, where n is the number of records. But remember, that extra level of placeholder or dummy nodes that are the leaf nodes, they're just an extra constant factor based off of this. And then on top of that, we just have each one of these attributes that we're going to add in. Each is just some number. And the idea is that since it's just some fixed size, we're okay. So this is just a simple modification. It's just another instance variable we're adding to each one of the nodes. So remember, we're just going to need to update the heights on insertions and deletions. And I'll talk more about this updating process as we go along. I'm going to slowly reveal it to you. So, where we're going to go with this. Well, I'm going to quickly give you a short algorithm for recomputing the height if ever we need to update the height at a given node. How's that sound, everybody? Is that clear? So like right now we're just trying to modify and update the heights at nodes. So I'm going to give you a very short algorithm that I'm not even kidding. This is going to be one of the shortest algorithms I'm going to give you in this course. So let me write it over here. We're going to, I'm going to show you how you can update the height, assuming that you actually have all these heights stored in the nodes. So as I'm erasing the board here, I have a question. As I annihilate the whiteboard eraser, that was amazing. Just annihilated with some fatality there. It fell pretty good. So where I'm going with this is, do we actually, if we're storing in all of the nodes, the height currently, do I need to update every one of the nodes' height or only the ones that are affected? Yeah, only the ones that are affected because I'm already storing the heights, right? So if ever I change the way the tree is, the only ones that are going to be influenced are the ones that are affected by some modification in the tree, which this will actually happen in the algorithms we're going to see in the next couple lectures. So here we go. So I'm going to presume that there's the ability for us to get the height and set the height, okay? And one other presumption I'm going to make is that setting the height is only called on internal nodes, but you can very easily modify this to allow it for leaf nodes. So here's the algorithm. I'm not even kidding. This is going to be a very simple algorithm. So algorithm, I'm going to call it recompute height. We're going to recompute the height. And imagine I give you some node P. So as input, I get node P. And as output, I'm just going to update. So it's just going to update the height for P. So I'm just going to remind you that this is going to assume P is internal, because we're never going to call this actually on a leaf node in any of our algorithms. Because what's the point of updating the height of a leaf node? The leaf height, remember, what's the height of a leaf node? It's 0. I don't ever need to update these. And our algorithms are going to be designed so you never have to. So here's the algorithm. So prepare yourself. So I'm going to update. So I'm going to apply set height on the node. So just as a reminder, remember that these are typically dynamically allocated. So in C++, whenever I write dots like this, I'm actually meaning follow the pointer. So P, I'm going to call set height. I'm going to now put in just the formula I gave you for computing the height of a node, right? So this should not, so I'll just remind you in a moment. So it's 1 plus the maximum of the following two values. P dot get left. So I'm just going to get the left node. And then I'm going to call get height. So I'm going to get the height. And I'm going to, the other value is going to be P dot get right. So I'm going to get the right child. And then I'm going to get its height. And then I take the maximum of these. This is a closed curly bracket here for the max function, and then I have a closed, I kind of squished it up here. The parenthesis closes off right up here. I thought I would do that for dramatic purposes. But when you actually look at this should look eerily similar to something we actually talked about some lectures ago, right? So we have the left and the right. Those are the children, right? Since this is an internal node, I have two children. Because it's a proper binary tree. I can guarantee I have two children. I have a left one, a right one, and I add 1 to it. We've seen this before, right? So I don't have to apply like our computation of the height like algorithm, like the one I showed you the other day. I could just apply this formula on any one of the internal nodes to update it immediately. So notice that this right here, now I have a question actually. Rather than me telling you it, what is the worst case time complexity of this operation? Can somebody tell me? So if I called this on a node, how long should this take in terms of big O? Yeah, so far I'm seeing constant time, which that should be not very surprising because it's just, these are just accessing attributes of our nodes, right? There's no recursion or anything like in our algorithm I showed you for general rooted trees. So the time complexity here is unsurprising. The time complexity is big O of 1 per node. So if ever you call this on a node, it's going to take constant time. If you try running this on every single one of the nodes in the tree, how long should that take? In terms of big O. Big O of n, yeah. So we want to avoid doing that, right? We don't want that to happen. Because if we update every one of the heights at all the nodes, it defeats the entire point of what we're trying to accomplish here, right? You can most certainly do it, but we don't want to do that. We want to only update nodes that are related to things that are getting affected by modifications in the tree. So the point here is now we have this mechanism for updating the heights. Now let's define what an AVL tree is. So before I can define it, I'm going to describe a property to you. So here we go. The AVL tree is a binary search tree that satisfies the height balance property. So it's a binary search tree. It's going to satisfy the thing we're going to call the height balance property, which now I'm going to define for you. Which is, I'm going to change this period into a comma, which is colon, which is for every internal node, P, the heights of its children differ by at most one. So that's what the height balance property is. I'm going to draw you a fun picture just to give you an idea what I mean by this. So just to reiterate, it's going to be that for every internal node P, the heights of its children differ by at most one. So here's a picture to give you an idea what this will look like. So if I give you any one internal node, if I examine the heights of its children, which we have a left one and a right one, which keep in mind, these could be leaf nodes, potentially. The point is, this is some internal node. And suppose that I had the height of the left child and the height of the right child. It has to be that if I take the absolute value of the following difference, that I take HL minus HR, this can be no more than 1 for every internal node. That's what the height balance property means. So we could call it an AVL tree if it's a binary search tree where it has this property. So naturally, like I told you, our goal will be for our AVL tree to maintain this property. So you might ask, okay, so where did this property come from? Well, it had to come from probably the mind of somebody when they're studying this very carefully. But you also will notice that as I'm sort of suggesting here, this property will have some interesting consequence for us. So first, before I proceed, are there any questions about what an AVL tree is? So I'll be showing you some examples of what these will look like shortly. So just remember, it's just a binary search tree with this other property too. So our goal will be to modify our insertion and removal such that it will ensure that this property is always going to hold. That's going to be our end game here. Because I haven't really told you what this is going to do for us, which I'm going to reveal next here. So I'm going to tell you a couple of neat properties if there aren't any questions about AVL trees. So the first thing I wanted to bring up is, and I'll make a note of this because it is quite relevant for what we're going to do here, is there's two properties I really want you to be aware of about AVL trees. Naturally, because we're talking about trees like this, you're going to find that the property I just described to you, where it's saying for every one of the internal nodes, it has to have some property. And this property depends on the children, so very naturally, you can ask the question, is every subtree of an AVL tree also an AVL tree? And the answer is yes. So I want to note any subtree of an AVL tree is also AVL. So it's also going to be an AVL tree. So this sometimes is very relevant for what we're going to be doing here. So just remember, we don't have to necessarily study the entire tree when now we have to talk about an AVL tree. We can look at any one of the subtrees now, and I can tell you, okay, that has to be an AVL tree too. So if ever I make modifications to the tree, I can make statements about the subtrees and say, okay, if I make this modification to something that was like the smallest subtree in my AVL tree, and if I correct that or something, I fix it or something like that, because I told you it's going to self-balance, right? Well, the consequence of this is if I can fix the small subtree, for example, then I can fix the overall tree. So the other part is going to be the following claim, and we're going to prove this together. So here's the claim. So when we impose the height balance property, we're going to get the following. The height of an AVL tree is at most 2 log base 2 of n plus 2. That's the claim. So I must stress that you can analyze this a little bit more carefully, like the structure of an AVL tree, but you're going to find that this will be good enough for us. Can anybody tell me why, if this was true, that this would be good enough for us? Why would this be good enough? So if I could prove this, what does this mean? Why would I be satisfied with just this and not like some... Yes, so notice that this function I just wrote up here, 2 log base 2 of n plus 2, is big O of log n. So if we can prove this, then we're good, right? Then I've done exactly what I posited to you. Then all of the work after that is figuring out how we're going to do those insertions and removals to make sure our binary search tree remains an AVL tree. Is that clear, everybody? So you'll find very often when you're studying these things very intricately, you think of some interesting, like you come up with this great idea, and then the question is, how do you maintain that it has this property? And very often in algorithm design, this happens all the time, where you study some problem and you notice that you could reveal some property based on some natural question that comes out of a flaw. In this case, we're trying to correct the balancing of the tree, and this is one interesting consequence. So now let's prove this. So we're going to be pulling out some properties that trees have to help us with this, okay? So I'm going to need your help. I'm going to need your help doing this. So I'm going to start off with let h be the height of an AVL tree, an AVL tree T. Now, question. Is T just any old binary tree, or is it a proper binary tree? Is it just any old binary tree, or is it specifically a proper binary tree? It's proper, yes. So I'm going to pull up so I want you to just imagine you have your list of properties that I gave you earlier, say a previous lecture, and I'm going to start looking at those and see if we can use them to help us. So T is a proper, I was about to say, I was about to write two P's. That isn't that kind of day today. Is a proper binary tree. So, the height can be no more than the number of internal nodes, right? We used this property at the beginning of lecture. Right, this is true for proper binary trees. So I'm going to use this fact. Now, this is the thing. And this is the strategy so I'm just going to give you an idea of the game plan here. What I would like to do is I would like to make the number of internal nodes as small as I possibly can to give a nice tight bound on H. So if I can relate the number of internal nodes to H using something like N at the end game, then I can relate H with N. So the whole trick here is I'm going to try to make this on the right-hand side as small as I can. So let N of H be the minimum number of internal nodes in an AVL tree of height H. So, like I said, I'm going to try to figure out how small the right-hand side can be based on in relation to H. So my goal is to find something that relates to eventually N. But we need to do some things in between. So you're going to see that it's almost going to be like I'm going to do a magic trick here where I'm just going to imagine I have a hat and I'm going to pull the bunny rabbit out of it. But the point is I need to get this set up so that I can appropriately bound the number of internal nodes, because we know that the number of internal nodes, because remember, what do I know about the number of records in relation to the number of internal nodes? What do I know about that? So this is what's going to be the bunny I'm going to reveal at the end of this proof. So I know you guys are the savants of this stuff. So what is the number of internal nodes in a binary search tree when I count up how many there are? So what is it in the data structure? So think back to what a binary search tree has. So what does it contain? It contains records that are in the nodes, right? But which ones have records in them? Do the external or leaf nodes do, or what? The internal ones do, right? So if I can come up with a nice bound that relates to the internal nodes, you know this will be this is certainly going to get bounded from above, or it can be equal to the number of internal nodes based on the number of records, which that's what N is. So just keep in mind that's going to be something I'm going to pull out at the end of the proof, okay? So right now we're going to focus just on the number of internal nodes and H, okay? Is that clear, everybody? So right now you're not going to see N for a little bit. I'm just going to try to massage this so that I can get something in relation to H, but also something about the internal nodes. So now you might ask, okay, so what's n of h? So let's talk about that over here. So this is where we're going to start. I'm going to start drawing out some AVL trees so that you get a flavor for how these tend to get structured. And remember, it's still a binary search tree, so it still has the binary search tree property. So there's nothing magical or anything. It's the point here is that it still will maintain the binary search tree property. So you can just put in you're going to put in keys if you'd like. You're welcome to. I'm not going to for the sake of this discussion. But the point I'm getting at is that the thing that matters in our discussion here are the heights of the nodes. That's what really matters here, at this stage, at least. Okay, so we're going to figure out what n is. So n of h, I want to figure out what this is. So let's start off with an empty binary search tree. That's what an empty binary search tree looks like. The height of this node is 0, right? So this would be what, if I gave you n of 0, which that would be the height of this empty binary search tree is 0, you would say that the height is 0, right? Pretty easy, right? Okay, now let's go to n of 1. So I'm going to start us off with a couple of these, and then we'll see what's happening here. This seems rather strange at first when you first start seeing me draw these. Okay. So if I wanted to make an AVL tree with as few internal nodes as possible, so my goal is to just make as few of them as possible. To get height 1, I need to just make sure I have one internal node, right? So that I can connect it up with children, so I can prop it up, so I can get that extra 1 of height. So remember, these are of height 0. This is of height 1. So the number of internal nodes this has for an AVL tree of height 1, the minimum number, it has to be 1, right? Now let's try 2. So let's try to find the minimum number of internal nodes I need for an AVL tree of height 2. Now remember, the whole idea here is that at every one of the internal nodes, it has to be that the heights of the left subtree and the right subtree cannot differ by more than 1. These are of 0, right? So remember, they're not going to differ at all, right? So that means that I'm also going to have a little bit of wiggle room. So for example, I can push some of the nodes over to one side, but I can't do it too much, right? I can push it over maybe by 1 level, like roughly about 1 level. So let's try doing that. Let's try doing that. So I'm going to start off with a root here. I'm going to have a leaf node, and I'm going to push one internal node just right about here. Now these, of course, are of height 0, right? This node has height 1. This has height 0, right? And that has height 2. But notice that we still have the height balance property, because at this node, notice it's 0 versus 1. They still differ by at most 1. And these, they don't differ at all, right? So we're okay. So notice that all I had to do to achieve this is by adding in 1 internal node. So hopefully you're getting the idea here. The whole idea is I'm trying to make as few internal nodes as possible. So n of 2 is equal to 2. But there's something kind of interesting happening here. I'm going to go to the next one here, and I'm hoping that you might see that I'm actually coming up with a blueprint for how I can always do this. So notice that, like, at first it looks like I'm trying to do something very delicate here, but actually, there's actually something very fascinating going on here that I haven't yet really said. So I want you to pay close attention for how I'm going to do n of 3, and I want to see if you can catch on to the pattern. So what I'm going to do is I'm going to start off, because remember, I want to figure out what n of 3 is. So I'm going to make an AVL tree with height 3 with as few internal nodes as possible. So I'm going to use the same idea. I'm going to try to lopside it a little bit. But remember, I can't just put 1 right here and just bog it down, right? Because it would be okay at this node, it would be okay at that node, but then it would be 0 versus 2, which is too much, right? That will violate the height balance property. So what I'm just going to do is I'm just going to start with something that looks kind of like this, maybe. But instead, I'm going to try to put 1 on this side to kind of balance it out. Pun intended. So let's, so I'm just going to start off with that. So I'm just going to put my 1 here just to sort of lopside this. And then I'm going to put this guy in, as I was sort of suggesting for my idea. And then now I can put in my new node that makes it taller. So these are of height 0, height 1. This one will be height 2. There's your height 3 node right there. So if we look at n of 3 is exactly equal to 4, right? Notice I can't do with any less, based on a similar rationale I sort of laid out here. Nothing formal, I just wanted to give you intuition with this. Does anybody see anything interesting going on here based on the way I sort of built this? I want you to look carefully at my pictures here. Is there anything that looks familiar to you? Anything at all? So remember, the whole idea was I was trying to introduce another node in, but to put it in, I needed to balance off one of the other sides, right? So that I don't violate the height balance property at the new node. Yes, that's exactly it. So look at the 2 previous trees. So look at this, The minute you see it, you're like, whoa, man. Whoa, look at this. So look at, for example, I have n of 3 here. So look at this. So there's n of 1. Here's n of 2. Well, look at it. There's what I drew for n of 1. There's the one I drew for n of 2. Right there. Does everybody see that? So I can go even further with this, right? So my prediction is I should be able to take these 2 pictures, put them beside each other, and add a new internal node. So let's see what happens if I do n of 4. So I'm just going to draw the 2 previous pictures. So there's n of 2. Remember, I'm doing this so that I can balance off one of the sides so that I don't violate the height balance property, right? At the new node I want to put, so this is the new one I'm going to tack on. So now this will be for n of 3, right? And I have 1 there. And let's see here. We got 1 here. Then we need 2 more. 2 more. I believe I got this. Let's see, 1, 2, 3, 4, 5, 6, 7. So if I look at n of 4, the answer is 7, right? So notice that I couldn't introduce this node, because let's look at the heights now. So this one's height is 1. Remember, these are 0, that's 2. This is 3, and this will be up to 4 here. Right? 1, 2, 3, 4, if I count up the number of ancestors that I have at the leaf node here. So, but the thing is, at every one of the internal nodes, I have to maintain the height balance property, right? So if I have 0 here, it's 1, 2. So it differs by at most 1. And here, it differs by at most 1, right? Based on the similar justifications I gave there. So I've actually given you the core ingredients for determining what n of h is. Does anybody see what n of h actually is? So if I were to say, so I'm not going to prove this for you. But here we go. Thus, for h is greater or equal to 3, I can actually define it based on the numbers for the 2 previous drawings I made. But each one of those is for a value of h, right? What are those 2 values for h? So if I try to write down a formula for n of h, what would that look like? Well, let's think about it. I have, for example, for n of 3, it was n of 1 plus n of 2 plus 1. So what would that look like more generally then for n of h? So n of h is going to be what? We're right on the cusp of it. So we know it's based on the two previous trees, right? So we know that each one of these, this is the value I'm going to have, and that one's going to be the other value I'm going to have, and that's how I determine n of 3, and I add 1 to it. Remember, just like I have over here. This is n of 2, whatever, this is the drawing I had for n of 2. This is the drawing I had for n of 3. So I have n of 2 result plus n of 3 plus 1 for the new internal node I add in. Yes, exactly. That's exactly what I'm looking for. That's exactly it. I'll write it in a similar way. So I'm going to write it, I'm going to start off with the smaller term first. You're going to see why in a moment, but it doesn't matter. So it'll be n of h minus 2 plus n of h minus 1 plus 1, right? Remember, this is the one that came 2 drawings ago. This is the previous drawing, and I just add 1 to it. So is this formula, did this come out of magic or anything, or does this make sense to everybody? So this is just the intuition behind it. So I'm not going to prove it for you, but this is actually the recurrence relation that actually describes the minimum number of internal nodes an AVL tree can have, where you can define its base cases for these smaller values here. So this is its value for h is greater or equal to 3. And you can define the base cases as we have over here. So any questions about that? Any questions at all? So now we actually have one key ingredient in the proof. Yes, it is interesting, right? That it does have a very interesting, that's a very interesting suggestion. It reminds me, yeah. So somebody is suggesting it reminds them a bit of the Fibonacci numbers. And that's interesting, right? In fact, I really find it fascinating you actually brought this up. The more sophisticated analysis for determining the height of the AVL tree is actually based on analysis that uses the Fibonacci sequence. So it's actually kind of related to using Fibonacci sequence. So it's actually, I like that you actually brought this up. So there actually is a tighter analysis for this claim that actually uses an analysis technique that's based around the Fibonacci sequence. So I like that you actually brought this up. So that's just a remark. It's more of a technical side note. If you ever go digging around for that claim, it's something that's about, I try to remember the constant off the hand. It's like 1.44 something. But the point I'm getting at is that it is very fascinating that it comes up. And the great thing is that structure itself was also helpful for the analysis. So I like that you brought this up. So you can actually take advantage of that fact if you do some more sophisticated analysis than we're going to do here. We're going to still do some trickery, but maybe not to go that far. We don't need to go that far. I like that was actually brought up. So now that we have a formula for the minimum number of internal nodes in an AVL tree of height h, we're going to take advantage of something that we know about this function. Now, this is actually where sometimes you might ask, Dan, why do we learn that calculus stuff? Why did we learn about increasing functions and all that stuff, say in first year? Why did we learn all about that stuff? Remember how we talk about complexity functions and we learned about a whole bunch of different kinds of functions, right? A lot of that stuff is very helpful for thinking about complexity, because oftentimes we think about it in terms of functions. Now, I'm going to pull out something that you probably were looking at, say, in calculus or something, or a class akin to this. And you might say, Dan, when would we ever need that property? Why would I ever need to care what an increasing function is? I'm going to show you an example where it actually can be helpful for us. So I have my formulation here for n of h. But I want to make an observation about n of h. So here's the thing. Notice that for each one of the values, I add 1 to it every single time. So if I were to try to plot out what the value of this each time, the shape of it, is it going to be wobbly like this? is it going to plateau like this? Or is it always going to go up? Now, I'm not claiming how fast it's going to go up, or is it always going to go up regardless? It's increasing. It's increasing. For those that really want to delineate, I'm going to say it's strictly increasing, meaning it's always getting bigger. Like the input, whenever I put a next value in for n of h, it's always going to get only bigger. It never gets smaller, it never stays the same. So we're going to use this observation about n of h. So n of h is strictly increasing. So we can make the following claim. So that means that n of h minus 1 has to be strictly greater than n of h minus 2. So that means that if I give you the input of this function and I subtract off 1 from h, this has to be strictly bigger than n of h minus 2. So we're going to use this fact. This has to be true for all h that I've described right here. Does everybody see that? So this is because every time I add 1, every single time, it never goes down. It always goes up, the value of n of h, as h gets bigger. So now we're going to use this fact to cleverly bound something here. So let's watch this carefully. So here's a trick I'm going to show you. And at first it's going to look like, Dan, what the heck are you doing? But you're going to see that I'm going to try to simplify down n of h by trying to come up with a nice bound on how many times n of h is going to get applied for its recursive parts on the lower side. So I'm going to try to make a lower bound on n of h. So watch this. Watch this. So watch this. So since I have that property, I can rewrite this as follows. So I can write n of h is strictly greater than the following. What I'm going to do is I'm going to just simply drop the 1. I'm just going to replace wherever I see n of h minus 1 with n of h minus 2. So that means I'm going to have 2 terms of n of h minus 2. But this, I can write out the definition of this, but I'm just going to drop the 1 because I don't really care about that right now. So I can say this is 2 times, so it's going to be strictly great. This is strictly greater than 2 times. I'm just going to expand this out, and I'm just not going to include the 1 in there because I don't really need it. N of h minus 3 plus n of h minus 4. So I'm just going to write out what n of h minus 2 is without the 1, because I'm not going to need that. So this is indeed true. I'm just going to take this, expand it out like this. I'm just going to drop the 1. It only makes it smaller. So now I'm going to apply the same exact trick. Wherever I see n of h minus 3, I'm going to replace it with n of h minus 4. So that means I have 2 n of h minus 4 times 2, meaning I have 4 n of h minus 4. So that means I can replace this, and I could say that this is strictly less than 4 times n of h minus 4. Do you see I can actually keep doing this? I can keep repeatedly applying this technique, where what I'm going to do is I'm just going to write out what this is. I'm going to drop the 1. I would have n of h minus 5 plus n of h minus 6. I can replace n of h minus 5 with n of h minus 6. Only makes it smaller. And I end up with another multiple of 2. And that means I get 8 times n of h minus 6. Do you see a pattern yet? Any pattern here that's sort of sticking out to you like a sore thumb? So notice that I started off with, I have like whatever this was, then I have 2 times whatever that thing is, with subtracting off a multiple of 2. Then I have 4 times h minus 2 times whatever that is. Then I have 8, which is another power of 2. So notice it's going up by powers of 2, right? So we can see if I could keep repeatedly applying this to some point, I end up with 2 to the power of I, for some value of I, times n of h minus 2i. So for each application of this, notice that this is 2 times 3, right? That's 2 cubed. 2 times 2 is 4. 2 squared is 4. So I'm writing out a general expression for this technique that I'm doing over and over again. I'm just trying to bound this appropriately. So I can conclude the following now. That is, n of h is strictly bigger than 2 to the power of h times n of h minus 2i. So now, and this has to be true because I always have to say when this is true, for any integer, I, such that h minus 2i is greater than or equal to 1. So now I have this general pattern that I can use. Now, akin to what we talked about previously, you know how we did this idea where I try to make it so I get the input to look like the base case, or at least one of the base cases? That's what I'm going to do here. So just like in our analysis for binary search, I'm going to pull off the same trick here. So it's not like it's coming out of the blue. It's the same trick. So watch this. So remember, I have n of 0, I have n of 1, and I have n of 2. Now, for the convenience in my proof, I'm going to try to make it so n of h, whatever the input is, I'm going to try to get it so its h is either 1 or 2. It makes the proof a little slicker, or at least in my opinion. But the thing is, you're going to see that all this is going to come out really nice. So what I'm going to do is I'm going to pick I such that h minus 2i is either 1 or 2, right? That would mean that I'm dealing with n of 1 or n of 2. Then, now what I'm going to do is I'm going to pick I. Now, I'm going to pick I in a very specific way, and I'll try to justify it for you, my selection of this. But I encourage you to think carefully about it. So at first, it's going to seem like I pulled this right out of like nowhere. It is actually closely related to the expression over here. So I'm going to pick I to be the ceiling of h over 2. So the ceiling around h over 2, and I'm going to subtract 1 from that. So I want you to think about if h was even or it was odd. So if it's even, for example, that means that 2, so if I have h minus 2i, well, if I put in the ceiling of h over 2 minus 1 like that, well, since h is even, the ceiling doesn't matter, right? So that means it's going to be 2 times h over 2, so those 2's are going to cancel. Then I'm going to be adding on an additional, so I'm going to have h minus h plus, in this case, it'll be plus 2, so I get h of 2. In the odd case, you'll end up with, I believe the input will be 1 in that case. But I want you to, if you're not convinced by this, I want you to try the 2 cases, when it's even and when it's odd. And you'll see that in this case, you'll either end up with 1 or 2. So feel free after class, just like fiddle around with this, or if you want to bug me after class, I'm happy to do so. So let's go with this value of I. So far we're doing okay. I just wanted to make sure. We're not quite out of the gate yet, but we're almost there. We're almost there. So now I've picked it, And now what I'm going to do is I'm going to use this fact based on having this right here. So let's wrap this up. Okay. So far we got the following. We got then for h is greater or equal to 3, we have the following. So watch this. So I'm going to plug in that value for I. Then I end up with this follow. So n of h is strictly greater than the following. 2 to the power of the ceiling of h over 2. Remember, ceiling, just as a reminder, ceiling means we round up automatically. We always go up to the next highest integer if it has a fractional part. If it's an integer, then, like if this ends up as an integer, it doesn't do any rounding. So for example, if I had 4 in here, 4 over 2 is still going to be 2, but if it was 5 over 2, then it would round it up to 3 because 5 over 2 is 2.5. It would round it up to 3. So now we have this. So I'm just going to plug in everything. H minus 2 times h over 2 at the ceiling plus 2. And so I'm just going to multiply that out for the sake of saving you a little bit of time. Then next we have the following. So now remember, this result is either going to be 2 or 1. Notice that if I just presume that this will be resulting in where the input is just 1, we'll see what happens. Because remember, what's n of 1 again? What's n of 1? And you're going to see why I picked this value. It's just 1. Yeah, exactly. It's just 1. It's just 1. So this is actually why I picked it this way. So now I could just say this is greater than or equal to the following. It's just, now remember, if I have this here, notice it's a ceiling. So remember, it will just round up that, and that only makes the exponent bigger, right? So I'm just going to drop the ceiling on that right now. So remember, if I make this so it's n of 1, so watch this. I'm going to take these two steps together. So I'm going to have the ceiling of h over 2 minus 1. This can be multiplied by n of 1, which we know is 1, right? So this could be this is going to be greater than or equal to 2 to the power of h over 2 minus 1 without the ceiling. This is because I'm only making it smaller by removing the ceiling function. But now, okay, so I have a whole bunch of stuff written here. Okay, I have the n of h, and I have this over here. Something that looks like a power of 2. Does anybody have any suggestions of what I should do with these? I have something that looks like an exponent on one side, way over here. I have something that is n of h. And remember, there's a relationship between n and n of h. Remember I told you about the bunny earlier? We're going to reveal that bunny soon. But I want to relate h with n at some point, but to get to n, I use n of h. So if I have an exponent like this and I want to get h, any suggestions? We've done this before. We've done something kind of like this before. Yeah. Somebody is suggesting that we take logarithms to both sides of the inequality. So let's do that. Let's try that out. We'll see what we get. So take logarithms to both sides to obtain the following. So we're just going to obtain that log base 2 of n of h is going to be strictly greater than, now remember, if I write out this in terms of a logarithm, what is this? So remember that is, if I were to just write this out, this would be log base 2 of 2 to the power of h over 2 minus 1, where h over 2 minus 1 is in the exponent. What is this equal to? What is that equal to? We're almost there. Yeah, h over 2 minus 1, because I can pull this out because of the power law of logarithms. Log base 2 of 2 is just 1. So this is just going to be equal to h over 2 minus 1. Therefore, let's put it all together. We got the very last line now. Therefore, we get that h, because remember, h is right here. As I mentioned, we want to relate h with n. So what I'm going to do is I'm going to multiply that left-hand side over there by 2. So I'm going to multiply everything I have here by 2. And then I'm going to add this opposing one, which will now be a 2. So minus 2, I'm going to add that to both sides, making it so I add 2 onto that side. So h is now going to be less than 2 times log base 2 of n of h, which is the minimum number of internal nodes an AVL tree of height h has, plus 2. But surely the minimum number of internal nodes that an AVL tree has cannot exceed the number of records, right, in the entire AVL tree. That is in fact the case, because remember, it's the minimum number of internal nodes that are possible for an AVL tree of height h, right? So surely this serves as a lower bound. So I'm just going to put that in. So now I just got 2 times log base 2 of n plus 2. And we're done. Look, there we go. We got the relationship we were desiring. And now the big consequence we have. So remember, the big idea here. We observe this height balance property. So this is something that it came up with. And it has an intuition behind it we're going to talk about next class. But when we think about this, we've actually figured out why, from the result of the height balance property, that an AVL tree actually has logarithmic height. So that's the point of this proof, is that together we found this out. So remember, the goal here that we get as a consequence of this proof is, so maintain the AVL tree, we get big O of log n time operations. So that's going to be our goal. We're going to start talking about that next day, how we're exactly going to do that. So we're going to stop right here. I thought this would be perfect. I'm going to give you back a little bit of time that I took from you the other day. And that being said, when we come back, we're going to talk more about AVL trees. So I'll say thank you very much and have yourself a beautiful day. I'll see you later.